Welcome to this explainer. If you've ever watched a speeding car, a drawn bowstring, or hey, even just the screen you're looking at right now, you are literally witnessing the mechanics of energy, work, and power in real time. Today we're going to decode these foundational physics standards to really understand the universe's ultimate rulebook. It's going to be a lot of fun.
Quick look at our roadmap for today. 1. The big three core concepts. 2. Kinetic and potential systems. And 3. Analyzing physics with actual data. Let's just jump right in.
Section 1. The big three core concepts. All right, so we start right at the source with standard PS.PHY.6. It challenges us to completely understand the relationship among work, energy, and power. And a quick fun fact here, this exact relationship dictates absolutely everything, from a single cell dividing in your body to a massive supernova exploding in deep space. So the text isn't asking us to just memorize dry definitions, right? It demands we actually understand how they interact in the real world.
To truly master this standard, we have to ask ourselves, what exactly is the relationship between work, energy, and power? You see, these aren't just isolated ideas floating around in some textbook. Think about it. If you do work on an object, you are transferring energy to it. And if you do that work quickly, well, you're exerting way more power. It's a constant, perfectly interconnected loop.
Actually, analyzing physics isn't about just rattling off terms. It's about defining these dynamic connections. Look at it this way. Work is the effort, energy is kind of like the currency that allows that effort to happen, and power is simply the speed at which you spend that currency. You literally cannot change one variable in this setup without mathematically throwing off the other two. Moving right along, Section 2, Kinetic and Potential Systems. Okay, standard PS.PHY.6.1 introduces a really crucial new requirement here, and that's using models. We aren't just observing broadly anymore. The standard commands us to use specific models to split energy into two distinct camps, kinetic and potential, within a system. But hold on, before we can even use those models, we first need to define the system. And that's really just the specific, contained area of physics we're observing. I mean, you can't calculate the physics of the entire universe all at once, right? You have to essentially draw an imaginary box around the bouncing ball, or the swinging pendulum, or the roller coaster car. That box, that's your system. It's absolutely crucial for keeping your data organized and accurate. Now, within our defined system, kinetic and potential energy are basically playing an endless game of tug of war. Potential energy is stored energy. Think of a heavy boulder just sitting at the very edge of a cliff. Kinetic energy, on the other hand, is the energy of motion. So that exact same boulder plummeting to the ground. As one goes down, the other goes up. To actually satisfy the source material, we followed these clear steps to transform this kind of abstract academic requirement into a measurable process. Step 1, you draw your boundary and identify the system. Step 2, you choose your model. Maybe it's a math equation, maybe it's a visual diagram. And step 3, you actually quantify the kinetic and potential energy playing out inside those boundaries. It is a perfect logical progression.
Which brings us to Section 3, Analyzing Physics with Data. Standard PS.PHY.6 brings the whole shebang together. It demands that we interpret hard data to prove those relationships we talked about back in Section 1. Notice how the text loops entirely back around to work, power, and energy. But now it adds the heavy lifting. We have to analyze and interpret the data, and we've got to do it both qualitatively and quantitatively. The crucial point here is that our explanation must be twofold. We have to perfectly balance descriptive, qualitative analysis with cold, hard, quantitative numbers. You simply can't have one without the other. If you only have the qualitative, the descriptions and concepts, well, you have no proof. But if you only have the quantitative, just raw numbers and math, you have absolutely no context. The standard requires both sides of the coin. To truly grasp this, let's look at a data framework. Check this out. As the numbers for work go up, the energy transferred naturally increases right alongside it. If you cut the time it takes to do that exact same work in half, your power output skyrockets. The math here is literally telling the story of the physical effort.
When we extract the qualitative insights from that data, we get these fundamental relationships that the curriculum requires us to understand. This is where we translate those raw numbers back into human language. Work translates directly into a change in energy. Power tracks exactly how fast that work is accomplished. It's a beautifully closed loop that perfectly summarizes the mechanics of our physical world.
So, it all really boils down to analyzing these three core interconnected mechanics: work, energy, and power. They are the true drivers of the physical world around us. Whether you're using qualitative models to track potential and kinetic energy in a closed system, or you're deep in the weeds interpreting quantitative datasets, everything anchors right back to this fundamental trio.
As we wrap up this explainer, I want you to consider how mastering these specific relationships allows you to decode the mechanics of the universe hiding in plain sight. Seriously, every single time you climb a set of stairs, you are a physical model of work, energy, and power. You are generating data. So I'll leave you with this. The next time you see a machine operating or a runner sprinting, look past the surface. Where are the boundaries of their system? What's the qualitative story of their movement? And how would you actually quantify their power? Keep analyzing, keep questioning, and thanks so much for exploring with me today.